So this example was basically looking at a hanging mass, which hanging mass we have seen has been held by a string. That string was elastic, so the string extended to produce an extension of 0.08 meters, which extension helped us to find the modulus of elasticity. And then that modulus of elasticity, we have ended up using it to find the tension in the second case when the extension has been 0.12 meters as a result of realizing new distance as 72 centimeters. Unless if someone has any question here. No question. I want us to go to the second category. The second category of there is a number here. I hope all of you have got the number from the what? You have got the number from the group and from that screenshot. You can also take a screenshot now. Let me have who there to read for us the question. Aisha Abdallah, read for us that question. Aisha Abdallah, read the question.
A light elastic string of natural length 29 is fixed at one end A and carries a mass of 3m at the other end. When the particle is hanging freely, a horizontal force of 3m Gn is applied to it. When the particle is in equilibrium, the string is inclined to the vertical at an angle alpha, and the extension of the string is 9. No, sorry. The natural length is 2a, and then the extension is a. Find the value of alpha. Show that the modulus of elasticity is 6 mg root of 2n.
Okay. So they are saying there is a horizontal force that is pulling the body, which is 3 mg newtons applied to it. And when the particle is in equilibrium, the string is inclined to the vertical at an angle alpha, and there is an extension of the string is a. But the mass attached is 3m, so it is 3 mg also. So with this regard, you will see that if we have pulled it away, it will displace an angle of alpha up there. So that means there is tension in this string. Now, there are various ways of solving this. We can solve this using Lamy's theorem of solving angles. We can also solve this using resolving of angles or resolution of forces and angles. So this angle here will be alpha. If that angle there is alpha, can you realize that the whole of this angle is 90 plus alpha? Do you see that? Then also this is 90, if you can see clearly. Then this one is 90 minus alpha. So the whole of that angle can be realized as what? The whole of this angle is 180 minus alpha. Because this angle here was what? Was alpha. So by Lamy's theorem, if I extract out the three forces, they will look like this. We have one force there, we have another force there, we have another force down. With this extraction, we can realize that one, this is 3 mg. This is also 3 mg. Then this is going to be the tension in the string. This is going to be 90. This angle is going to be realized as 90 plus alpha. Whereas the whole of this angle is going to be 180 minus alpha. So from Lamy's theorem, it states that one force, for example, tension, out of the sine of the angle opposite to tension, which is 90, is equal to 3 mg out of the sine opposite to 3 mg, which is sine of 180 minus alpha, is equal to the other 3 mg out of sine of 90 plus alpha. Who is the trig machine here? The trig machines I have, can we have who? Let me check out people here. Hadija, what is sine of 90? Hadija, what's sine of 90? Mugera Stephen, when I use green, you can't see. Can I use what? Blue? Or red? Eh? If I use red, I think it's okay. Let me go back to our red. Hadija, what is sine of 90? Elizabeth Magala, what's sine of 90? One. Okay. Then we have Chasimile Praise. What is sine of 180 minus an alpha? Chasimile Praise, what's sine of 180 minus alpha?
It's alpha.
Yeah? It is? Sine of 180 minus an angle, what do you get?
Sine alpha.
Sine of alpha. Mugera Stephen, sine of 90. Sine of 90 plus alpha, what do you get? Mugera. Sine of 90 plus alpha, what do you get? Which means people should check on their trig. That is why I've decided to check people here. Eh? Your trig is not steady. Kauthara, what is sine of 90 plus alpha?
Plus alpha.
But I call girls' names boys' answer. I call boys' girls' boys' names girls'. I don't understand. Are you saving yourselves? Okay. Now, with that reason, I can relate the second two terms. That is 3 mg out of cos alpha is equal to 3 mg sine alpha.
Excuse me.
Yes, please. Yes, you excused?
Sir,
Uh-huh.
I beg your pardon on how like we drew the diagram.
Hey. Read for me the question, sentence by sentence. Hello? The person who asked the question.
A light elastic string.
Yes.
Yes, teacher, I'm reading.
Okay, go
A
ahead.
light elastic string of natural length. Sir, I don't know what that digit is.
2A.
Of natural length, yeah, of natural length, 2A is fixed at one end A.
and carries a mass of 3 meters at the other end. When the particle is hanging freely,
carries a mass of 3m on the other end.
When
it carries a mass of 3m on the other end.
Yes.
Proceed.
When the particle is hanging freely, a horizontal force of 3 mg newtons is applied to it. When the particle is in equilibrium, the string is inclined to the vertical at an angle theta, and the extension of the string is theta. Is that A?
Is A. Now look at me in the diagram. I mean in the what? Not in the diagram. You see this particle? The plug of this TV set. It is hanging.
Yes, teacher.
When I apply a horizontal force, I'm putting it to the side. Yeah. But if I put it to the side, remember, this horizontal force is now acting as the 3 mg. But also this body has its own weight acting vertically downwards always. So that is how the diagram came about to look like that. And if you look, remember equilibrium of forces on bodies, there are conditions we looked at which had hanging masses, which we discussed. If you do not see some of those items, I will ask you to visit in my YouTube channel and see some of those conditions of equilibrium of forces, and also look for Lamy's theorem under my YouTube channel. Yeah, you'll see more examples on this that can always guide you on how the sketch comes out to be like that. Okay. In case of any other concerns, then you get to my inbox. All right?
Yes, teacher.
Okay. So when you reach here and simplify, we shall get tan alpha is equal to 1. And our alpha is actually going to be 45 degrees. So the first question said, find the value of alpha. We have got alpha. The second question says, show that the modulus of elasticity is equal to, show that lambda is 6 mg root over 2 newtons. Oh, Elizabeth is asking me, but teacher, why are we using Lamy's theorem and we are not using resolving? It's okay. Lamy's theorem is a shortcut. Yeah? Elizabeth, perhaps you sound like you don't know about Lamy, but Lamy states this. If you have 3 forces, 3 forces like this, P, Q, R, and R is opposite to theta, P is opposite to alpha, and Q is opposite to beta, then P over sine alpha is equal to Q over sine beta is equal to R over sine theta. But if you're interested in resolving, it's okay. Let us resolve horizontally. Horizontally, we shall have 3 mg is going to be equal to T sine of alpha. Then vertically, we shall have 3 mg is equal to T cos alpha. Here you might see it is easy because of this resolution being very direct. When you divide Roman 1 by Roman 2, and you get tan alpha is equal to 3 mg over 3 mg, and you get the same answer. But you'll find other interesting forces which are not obvious like this one, and they can confuse you very well. So a one who has borrowed Lamy would be better. Now the question said, find the modulus of elasticity. Now, why do we need the modulus of elasticity? From here, you can see that you can get tension from where? Tension is equal to 3 mg over cos alpha, whether using the second method or the first method. So this is the same as 3 mg out of 1 over root 2. Because cos of alpha is cos of 45. Do you realize that this is actually 3 root 2 mg as our tension? What if someone had used the one for sine, or T sine alpha is equal to 3 mg? This would be T is equal to 3 mg out of sine 45. The answer would still be the same, which is 3 mg root of 2. Because for sine 45 is the same as cos 45. Now, furthermore, they want us to find the modulus of elasticity. To find the modulus of elasticity, we shall need to get to this. Remember, tension is equal to modulus of elasticity out of the original length times the extension. Look at the original length. Do you remember the extension? The extension was given as A. So therefore, one can say lambda out of 2A times A. With this A and A, they can be lost. Then we shall have lambda out of 2 is actually equal to the tension, which tension is 3 root of 2 of mg. When I cross multiply, I will finally confirm that lambda is 6 root 2 of mg newtons. Hence proof. And that is our answer. Unless if someone has a question on this number, before I can adjust to another number. Someone has a question, please you raise it, and I see how best I can help. Which is the most appropriate color? And people are saying, people complain of green, of red, of yellow. No, red, I think red, no one.
Red.
Red, eh? Okay. Shall stick to red.
Red or blue.
Okay. Any questions here? I hope now the solution is clear. So take a screenshot. Only one person has sent the work, guys. I told you to convert the work into PDF. We are going to use our WhatsApp channels for marking. The thingy, the Google Classroom does not facilitate marking using a laptop. It wants to mark using a phone. So I would rather because you can't even make comments there. I would rather we convert the work to PDF and send it, then shall mark it by WhatsApp. Opio has done it. The rest are still failing to upload the work.
Teacher, I thought you told us to send to the other number that you gave us.
Yes, did you send?
Yes.
Only, okay, did you send today morning? Yeah?
No, at night.
Yeah, by night we have not yet received. Okay, I'll check. Okay, are we done with the screenshot, guys? There is another number there. Question 3 from the WhatsApp group, if you have it. Why can't I go back? Question 3 is right here. And we have Opio Andrew, read for us this question.
Strings SC and BC are both of natural length 5L. SC is inelastic while BC as a modulus of elasticity lambda. A and B are attached to 2 points in a horizontal line distant 5L apart. A mass m kg is attached to C, and the system is in equilibrium in a vertical plane with BC of length 6L. Find value of lambda. Hence show that the tensions in the strings CA and CB are 3 out of 4 mg and 7 out of 20 mg respectively.
Okay, thank you so much. Hope everyone has the question. You can screenshot that because our solution won't look nice and won't be fitting on this page. That's why we go for the other screens. So here we are. To start with, you have said this. Oh. You have said these two strings are attached to the same point, the same level. We have a point here at A and another point here perhaps at B. And on connecting them, they are going to look like this. So we have a mass here attached to these strings where they are connected. This mass has a weight mg. We have a point A right here. We have a point B right there. And we have been told that we have strings SC. So this is where point C is. Then BC. And then they have said SC is inelastic. That means SC does not extend. It has no modulus of elasticity. Whereas BC has a modulus of elasticity. And these strings are both of natural length 5L. So this one has a length of 5L, but this one will have a new length because it has extended because of the weight which has been put there. Yeah? So this one can experience a tension T1. This one can experience a tension T2. Now, my friend who was saying we resolve, here you see that Lamy can summarize this very fast, but as well we can resolve. That was a little bit. We can also resolve as we shall see. But now, according to this regard, you will see that if this is theta and this is what? Alpha, then horizontally, let me illustrate the vertical lines with another color, please. Bear with me. Horizontally and vertically, you will discover that this is actually what? Alpha, and this is actually what? Theta. Then this is 90. This one is also what? 90. Okay? So with that sense, we can have whatever we want to discuss and proceed. So they told us they were placed a distance of what? 5L apart.
5L.
So this is 5L apart. If this is 5L apart, remember this string this side has extended. This string this side, when it extends, it gets a new length we don't know. That means if it gets a new length, the whole of this angle and this angle, they are the same. Why? Because this distance and this distance are the same. So they form an isosceles triangle. Are we still together? We are interpreting the diagram. Now,
Which I beg your pardon?
can I extract out something? Let me extract out a triangle. I was saying that if the triangle looks like this, okay, We have seen this is 5L, okay? This is also 5 what? L, okay? But this length is not 5L because this string is extending, BC is extending. So we have assumed the BC has a new length L prime because of the extension. Then we shall have this as alpha. We shall have that as alpha. We agree? We agree? Pardon?
I would beg your pardon on how you extracted out the triangle.
And I'm looking at A, B, and C. There's something I had not read. The gentleman who read must have read this. At equilibrium, BC was 6L. Do you all have that in the book, in the notes, in the question? So we know the distance, BC. They are saying find lambda. So if we know BC is L, BC is 6L, we can use the cosine rule and say 6L squared is equal to 5L squared plus 5L squared minus 2 times 5L times 5L cosine of theta. Because I want to find this angle theta. When I find theta, I can lose L throughout. This is 36L squared is equal to 50L squared minus 50L squared cosine of theta. We can lose the L squared throughout by division. And then finally we shall have 36 minus 50, you get a negative 14 is equal to negative 50 cos of theta. Can someone get us theta straight away? Okay, just get me cos theta. Cos theta is going to be 7 out of 25. So if cos theta is 7 out of 25, we can get other ratios of theta. So if this is theta, this is 7, this is 25. 6 to 5 minus 49, you get 576, and this is 24. Now, we can get sine theta. Since we can get sine theta very comfortably, yeah, then we can as well get other angles. For example, we can get angle alpha. That is angle theta. Can we estimate angle alpha? Angle alpha, I can either use, this side of point B or the side of point C. Let me use the one for point B. Point B, I'll have 5L squared is equal to 6L squared plus 5L squared minus 2 times 6L times 5L cosine of alpha. Now with that, I can get, all these ones are squared. So this is 25 L squared is equal to 36 L squared plus 25 L squared minus 60 L squared cos of alpha. This will realize what? The 25 can die off. Shall have 36 is equal to 60 cos alpha. Cos alpha will give me, by 4, you get 9. By 6, you get 6. By 6, you get 10. So it gives us 3 out of 5. So with this 3 out of 5, we can extract out the ratios of alpha as 3, 5, and 4. Now, with that, we need to get the tensions. Why I needed those ratios? It's because I'm going to come to a point here. Look at these forces, they're acting like there are three forces acting on a system. If three forces act on a system, you can either resolve or you can use Lamy's theorem. So Elizabeth, this is where Lamy becomes more interesting. Now this is alpha, okay? This is 90 plus alpha. Then this one is 90 plus theta. So I'll have T1 over sine 90 plus alpha. Next time I'll assume you are mature. I'll just use cos alpha. Then T2 over sine 90 plus theta. Okay, is equal to mg over sine alpha. The first question wanted us to find the value of lambda. Okay, not yet, but I can get T1 from where? From mg over tan alpha. I relate this one with this one. The upper part becomes cos alpha. When you take cos alpha down, it becomes sine alpha over cos alpha to give us tan. With that, I can get T1 as mg. What is tan alpha? Tan alpha is 4 over 3. So 4 over 3 will give me 3 out of 4. But this T1, it is not extendable. It was inelastic, so you cannot use it to find lambda. So ideally, you should have found only T2. So can we get T2? But I have to show you also how to get T1. You never know, next time both of them will extend. Actually, the numbers I gave you from Boston, they were extending both of them. So you need to check them out now. So T2 will give us mg times the cos of theta divided by sine of alpha. You realize that this is going to give us mg. Cos of theta is 7 over 25. Divided by sine of alpha, which is 3 out of 5. By 5 once, by 5, 5 then. Tension T2 will confirm 7 mg out of 15. But 7 mg is supposed to be equal to lambda out of the original length times the extension we have produced. Now, remember the question. Who can read for us the first statement of the question? It says, strings SC and BC are both. Do you hear that statement? Are both of natural length 5L. If they are both of natural length 5L, it means L naught was 5L. But at equilibrium, we got a new length, which was 6 what? L. Do you see that you can confirm the extension as L? Don't be like zero-star students and you don't put there and you start saying 6L minus 5L. We are advanced mathematicians. We all know that extension is natural new length minus original length. So you subtract straight away, get the answer. We are now ready to substitute. We shall have 7 mg out of 15 is equal to lambda out of 5L times L. Vamush the L by 5 once, by 5 thrice. Lambda is equal to 7 mg out of 3. And these are newtons. Yeah? There is the 7 mg. Have I made a mistake? Wait. This was 25. This was 3 out of 5. 3 out of 5 was for alpha. Eh? Oh, guys, how come no one saw this? This was sine alpha, right? Sine alpha is 4 over 5. Sorry. Sine alpha is 4 over 5. I hope you've seen that error I made. So this is 4 out of 5. So the 4 meets the 5 to confirm a 20. When it confirms a 20, the 20 is divided by 5 to get a 4. And our answer is 7 out of 4 mg. Okay. So you can have that adjustment. Remember, take screenshots all the time. So the first question said, find the value of alpha. Hence, show that the tensions are, we have already got the answer. Tensions are 3/4 mg, correct. 7/20 mg, very correct. We have seen this one, it is here. One may say, but teacher, what if for me I wanted to resolve? My friend Elizabeth wants resolving. Resolve horizontally. You will have T2 cos alpha is equal to T1 cos theta. Then vertically, there is trouble there now. That is why Lamy was important. Now let's check here vertically. When I resolve vertically, this is what I will attain. T1 sine of theta, T2 sine of alpha. So we shall have T1 sine of theta plus T2 sine of alpha. They should both give me the weight. Now, if your algebra is poor, your world has come to an end. Why? Because you need to substitute carefully that T2 cos alpha is 3/5 is equal to T1 cos theta is 7/25. By 5 ones, by 5, 5. You see that T2 is actually 7/3 T1. Yes, new equation star. Then the second one, T1 sine of theta is 24/25 plus T2 sine of alpha is 4/5. It will give us mg. But I can substitute for 7/3 T1 where I have T2 and I'll realize T1 times 24/25 plus 7/3 of T1 times 4/5 is equal to mg. Algebra, LCM is 75. 75 divided by 25, the answer is 3. 3 times 24, the answer is 72 T1. 15 divided by 75, the answer is 5. 5 times 28, that is 140. I guess, confirm with the calc, is equal to mg. Then 72 plus 140, the answer is 212. T1 is equal to 75 mg. So T1 will give us something is wrong. Should give us 75 mg out of 212. Yeah. 5 cannot have a 2 at the end. Never. It either has a 5 or a 0. If I divide by 75, someone divide 15 by 212, what do you get? No, 25 by 212. It is impossible. It's supposed to be 225. Hey, wait, 25 divided by 75, the answer is 3. 3 times 7, 24, 60, 72. Then 5 times 7. Have I made an error there? They should give us the same answers. So Elizabeth, this is why we borrow Lamy. Because resolving comes to a point where it is lengthy and you have so many simultaneous equations to handle. Okay? Why don't people try it out? Try out this resolving part. We have resolved here correctly and here. The only challenge is now algebra. I substituted for T2 cos alpha, which is 3 out of 5, correct. Cos theta was 7 out of 25, correct. Oh, yes, I missed 3 times the 5. This was supposed to be 15. Is that true? So if that was supposed to be 15, this was supposed to be over 15. So the LCM is 75, which is okay. Happy to remain with the 28. Then 75 here becomes 72. 72 plus 28, the answer is 100. We are back on track. We are back on track. We are back on track. So this was over 15. This was over 15. This was 28. This is 100. T1 over 75 is equal to mg. So T1 was equal to 75 here by 25, 3 by 25, 4. Same answer. We have arrived. Then you get this one and take it back here. Then you get T2. Hence, the solutions will be the same. Someone was saying, excuse me, sir, please go ahead and ask a question.
Teacher, it's okay, I've seen it.
Okay, thank you. Any other concern, guys? Please don't hesitate if you have a question. So those numbers I sent you, which we are requiring some concepts of, there are some numbers I sent which we are requiring a bit of some knowledge on what? On those diagrams. You can now visit them. Then some numbers I sent had energy in them. It is after these examples that I'm happy now to introduce energy. So people can first screenshot that before I introduce energy. Okay, are we there? Don't forget to go over these examples again in your free time. That's the best way you can understand these concepts, right? With this knowledge now, people can start visiting question banks as well to see how far they can go with these numbers. Okay.
Sir, you first unmute.
Suppose a material of natural length L0 is stretched by a force F through a distance delta x or small change in x, then the work done in stretching the material can be got from the small change in work done is equal to force times the small change in the distance you've covered, x. Though work is normally we know work is normally got from the definition, force times distance. So if the work becomes very small, it means that the force is constant, but you're changing the distance you are moving. So the total work done, in stretching a material from x is equal to 0 to x is equal to E is given by work done is equal to the integral from 0 to E of F dx. But remember, force we saw is equal to lambda out of natural length times x. So the work done will be equal to the integral from 0 to E of lambda out of L0 of x dx. So this will give us lambda out of L0 integral from 0 to E x dx. And here everyone is an expert. So we shall get lambda out of L0 of x squared out of 2 from 0 up to E. Therefore, work done shall be lambda x squared over twice L0. So the work done in stretching an elastic material is always given by this expression. Okay? Now, this work done, the work done in stretching a material is stored as elastic potential. Stored as elastic potential energy. Sometimes we call it EPE. Also, we have another note. The work done in stretching a material from extension E1 to extension E2 is given by work done is equal to lambda E E2 squared over 2L0 minus lambda E1 squared over 2L0. That is assuming E2 is greater than E1. So this would give us lambda out of 2L0 into E2 squared minus E1 squared. In case you are not stretching it from 0. Okay. So those are the two definitions for work done or for energy stored in an elastic string or spring or material. Yes, please.
Like for the first definition, don't we have to substitute the x squared with E?
We have substituted. Aren't we advanced a little? Okay. You want me to say lambda E squared over 2L?
Teacher, no, the final.
Yes, my bad, sorry. This was supposed to be, yeah, you're right. We have to substitute. This is equal to E squared. But also some books you'll find them having x squared. Others you'll find them having this. Or there are various methods of deriving that work done. In physics, we shall talk about them, those of us who offer physics, but in math, you can just stop there. We just need only the equation. All right? So let's have an example. Have people taken the screenshot? An example. An elastic string of natural length (0.3 meters) is stretched through by 4 centimeters. Stretched through 4 centimeters. It is stretched through 4 centimeters by a 1 kilogram weight. By 1 kilogram weight hanging on it. Find the work done in stretching the string from a length of 0.35 meters to 0.42 meters. So remember these questions, sometimes they first give you some conditions to help you find lambda. So they have said an elastic string of natural length L0 is 0.3 meters, is stretched through, the first extension is 4 centimeters. By a weight of 1 kilogram, 1 kilogram weight. So 1 kilogram weight means the force in the string is going to be 1 G-Newton. So if you have a string and it has been stretched through that distance, which is 4 centimeters, it has a tension here, then at equilibrium, the tension is equal to mg, which tension is lambda out of the original length times the extension. So the m is 1 times 9.8 is equal to lambda, we don't know, out of 0.3 times 0.04. We can comfortably get the modulus of elasticity as 9.8 times 0.3 divided by 0.04. what is lambda? Someone realize lambda?
$73.5.
Lambda is 73.5 newtons. Find the work done in stretching the string from there to there. We have seen this work done can be got from lambda naught out of 2 original lengths into extension E2 squared minus extension E1 squared. Aine wants to take a screenshot for the previous work. There you go. Okay. So work done would be equal to the original length. I mean, modulus of elasticity is 73.5 divided by 2 times 0.3 into now the new lengths. Look at these new lengths. They are not the new extensions. The original length was 0.3. So the new length here is 0.12 squared and 0.05 squared. Can someone press the calculator? Because E2 can be got from 0.42 minus 0.3, 0.12. E1 can be got from 0.35 minus 0.3, 0.05. That's how I've realized them. So someone get me the answers. What answer do we get? $1.457.8.
1.4578.
Correct. 4578 joules. Okay. And have that down. We have 5 minutes. This time around, I want to surprise economics. And I have questions. I will not start a new number, but I'm going to tell you the other numbers and you check them out. Then now, the other numbers also which are vertical, which I expect to take a look at, which I had sent. I'll come back and visit some of them, I think, next week. So you can keep sending me those you feel that are a little bit challenging that you could land on. Questions? there are these ones. Starting from this one, let me give you a model of the approach of the number and you try it out. Okay. If no questions, I think we can call it a day. I'm
Have a good
requesting
day.
for the number. Chasimile, the number where you send the work. You're not on the WhatsApp group, eh? The number where you send the work. Yeah, we are receiving, the work is coming in. We have started seeing the work. It is 0701 21 58 58. Okay, guys, thank you for attending and have a good day.